Welcome back to Physics 152 Online. We're starting a new section in the course, and the motivation for this goes back to what we did when we were studying mechanics last semester. In mechanics, we found that you could often solve problems using Newton's laws of motion. If we know the forces on an object, then we can calculate its acceleration. From the acceleration, using simple calculus, we can find velocity. From velocity, we can find position. And that's the ultimate goal, to find the position of an object as it moves as a function of time. Then we turned to a slightly different formulation and found that we could solve many of those same mechanics problems, sometimes more easily, using energy methods. So that's what we're going to do for electrostatic forces. We're now going to move from talking about electric forces and fields to talking about electrostatic potential energy and introduce and define a new quantity that's called the electric potential. The symbol for that is V. So, in electrostatics, using these energy methods, we will need to define this new quantity, the electric potential, and especially the electric potential difference between 2 points in space. Now, as you might imagine from the names, electric potential is similar to potential energy, but they're distinct, and we'll see the relationship in just a moment. Delta V is difference in electric potential. Later we'll see that in the context of electrical circuits, this is often called the voltage. Then electrostatic potential energy difference is delta U. So in order to understand why we want to define this new quantity delta V, let's look at a specific example and see what the problem is. The potential energy difference between 2 points turns out to not be the same if we look at charges with opposite signs. So here's a specific example. Imagine that we have this bottom charge plus capital Q, and if we release another positive charge plus little q at a point near the larger positive charge, it's going to be repelled, so it will move away. And using our understanding of potential energy, it will move on its own from a higher to a lower potential energy. Now imagine the same situation where there's this positive charge plus q, but with a negative q in its vicinity. The negative q will be attracted toward it. So if we release it at the upper point, which is a larger distance away, it will feel a force towards the positive charge, and it will move from a position of high potential energy to low potential energy. And comparing the two sketches, we can see that the positive and the negative charges have different perspectives. One of them thinks that the high potential energy is close to the positive point charge. The other one thinks that high potential energy is further away. And they're both correct, but you can see that this situation is a little bit less than satisfactory. We'd like to come up with a quantity where the positive and the negative charges could agree on the difference. So that's the motivation for defining the electric potential difference between 2 points. We just take the potential energy difference, delta U, and divide by the charge. So in this case, we see that both the positive and the negative charges agree on which of those positions has high potential and which has low potential. And so just to go back for a moment to that sketch, we see that the high potential will be a point close to a positive point charge. The low potential will be a point further away from a positive point charge. All right, so that's our definition. Now recall, we can expand on this definition by using the relationship for the potential energy difference when there's a particle under the influence of a conservative force moving between two positions. You might remember this definition. We define potential energy as minus the work done by a conservative force when that object moves from an initial to a final point under the influence of a conservative force F. And dl is just the infinitesimal displacement vector along the path. One of the interesting things about this quantity, if we have a conservative force and we can define this potential energy difference, we'll find out that it only depends on the initial and the final position, and not the specific path that takes us from one to the other. So now we know if we have a charge Q in the presence of an electric field E, that this F can be replaced with Q times E. So if we do that here, we then realize, well, the Q is a constant. It doesn't change along the path, so it can come outside the integral. And now we have delta U is equal to minus Q times this integral, and we see from the definition up above that in order for the definition to be true, this integral minus this integral must be the quantity delta V. So here is the general relationship that connects the change in potential to the electric field operating on a charge as it moves between 2 points. And we will use this in a moment for a specific case. First of all, though, let's talk about units. Okay, the units for potential or potential difference is the volt, which you can see is a joule per coulomb. And we also then, rather than using joules for energy units, when we're dealing with small particles like electrons or protons, such as we find in atomic systems, rather than using joules, we define a Newt unit, because joules, the amount of energy expressed in joules for these systems is really tiny. So we'd rather have something that doesn't have a very tiny negative exponent connected to it. So what we define is we take this expression for U and delta V and Q and use it to define a new energy called the electron volt as an energy unit. And the electron volt is exactly what it says. It's the charge on an electron, which is also the charge on the proton, times the potential difference of 1 volt. And so those two multiplied together gives us an energy unit in electron volts. And we will use this in some of the homework problems in this part of the course. The conversion factor then that takes us between joules and electron volts, you can readily see is that 1 electron volt is 1.6 times 10 to the minus 19 joules. And this conversion factor just happens to be the magnitude of the charge on an electron or a proton. All right, so let's use that expression that we just learned a couple of minutes ago to calculate the potential difference between 2 points in the vicinity of an electric field. And we'll use the special case of a uniform electric field. Uniform meaning every point in space has the same electric field magnitude and direction. So let's first calculate the potential difference between A and B, where the path is simply a straight line connecting A and B, and the infinitesimal displacement vector is dl. After we do that, then we'll look at the same quantity between B and C. Note that points A and B in this diagram are a distance little d apart from one another. Now I said a minute ago that we could easily do this calculation on any path and it would give us the same answer. But some paths make the calculation easier than others. So we'll always pick the easiest path, and here it's natural to pick a path that will be parallel to the electric field vector. So delta V is minus the integral from A to B of E dot dl. And notice in this path, E and dl are parallel. So E dot dl just becomes magnitude of E times dl. Now we notice for a uniform field that E comes outside the integral, and then what's left is simply the sum of all of the dl distances traveling from point A to point B. And we can see if we add all those arrows up as vectors, it just, they're not really vectors, but if we add up all the displacements, the distances, they just give us a distance d. And so that integral simply gives us d. And notice what's interesting about this, it tells us not only the magnitude of the potential difference, but it also tells us that the potential at point B is less than the potential at point A. And the general rule we see is when you're traveling along the direction of an electric field line, you're always moving from higher to lower potential. So now let's do the same calculation for the path going from B to C. And notice here we also have a very simple calculation if we pick the path straight down, which is perpendicular to E. So E and dl are going to be exactly 90 degrees apart. The cosine of 90 is 0, and so that gives us 0. That tells us that for this path and all points along it, if we extended that line up and down, as long as it's a perpendicular line to the field lines E, then we would find the potential would be the same everywhere on that path. So VB is equal to VC. Now let's use that same formula for calculating the potential difference between 2 points, but let's use it in the case where there's a non-uniform field. And we'll use the case of a point charge. We know an expression for the electric field of a point charge, so let's imagine that we start at point A and move to point B along some arbitrary path. And we want to know what's the potential difference. We expect that it should not depend on the specific details of the path, and we'll see why that is in just a moment. So this calculation is not nearly as easy as for a uniform field, but it's not really that hard either. So how do we set it up? First of all, we pick a displacement vector at some general point along the path from A to B, call that dl, and then we draw in the field line. And if the point charge plus q is here, along a line that comes from that, the field points away, because this is a positive charge. So E and dl have an angle theta between them, and so E dot dl will simply be E times dl times the cosine of theta. Now, that still looks like a pretty imposing challenge, because as we go along this path from A to B, two things are happening. The electric field direction and magnitude are changing. So this E cannot come outside the integral. Also, the angle theta changes as we go along that line, so we can't pull the cosine theta term outside the integral either. So how do we proceed? And what we notice is that this dl cosine theta has a specific meaning in the context of this problem. Look at the diagram here. If we drew a right triangle with dl as the hypotenuse, and then looked at dl times the cosine of the angle, that would be the distance associated with dl that points along the direction of the field, along the radial direction. So you can think of dl cosine theta as being the projection of the dl length along the direction of E. And we will call that dr because that happens to be the radial direction in this problem. And if we replace dl cosine theta with dr, in other words the radial component of this displacement along the path, then it becomes a much simpler integral to evaluate. The electric field becomes kq over r squared, because we just want the magnitude of it here at this point, a distance r away from the point charge. And then dl cos theta becomes dr. And now look, we have a very simple integral. We realize now the variable of integration is the distance r, and kq over r squared dr. Well, integral of dr over r squared is just negative 1 over r. So the minus signs cancel. We evaluate the limits of this, and we get that the potential difference VB minus VA is KQ over RB minus KQ over RA. But it would be nice if we could just write down an expression for the for the electric potential at a particular point in the vicinity of this point charge. So if we just pick some arbitrary point a distance r away, what would the electric field, or what would the electric potential be? And what's suggestive, if we look at this equation here that we've derived, if we associate VB with the first term and VA with the second term, then we can see that there's a very natural identification. And if we do that, then we can define the potential in the vicinity of a point charge as k times the point charge over the distance r. Two comments about this result. Notice that it's a scalar, it's not a vector. So calculations that we do with the electric potential will often be easier than calculations that we do with the electric field near a point charge. Secondly, this definition already implies that we've chosen the potential to be 0 at a distance infinity away from the point charge. Because if r gets very, very large, then v goes to 0. So realize when you use this equation that it's always relative to a potential being 0 at infinite distance away. So this also, by the way, in just a few moments we'll talk about equipotential surfaces, since we see that at a certain distance r away from a point charge, the potential is exactly the same as long as that distance doesn't change. So what kind of surface has the same distance away from a central point? And that's a sphere. So it turns out that spherical surfaces have constant electric potential near a point charge. All right, we can now use our result that we just derived a moment ago for point charges and the connection between potential energy difference and potential difference to solve for the electrostatic potential energy of a system of charges. And first, we'll imagine doing this for a pair of charges, and then we'll add a third charge and get to see how the result generalizes. So here's the practical question. We have a charge Q1 sitting at a certain point in space, and we want to ask, how much work do I have to do to bring a second charge Q2 from an infinite distance into the vicinity of charge Q1? The way we're going to do this is by doing that calculation, first talking about, well, what's the difference in potential energy from the initial position, which would be infinitely far away, to the final position at a location R12 away from charge Q1. And that's easy. Here's the definition of potential energy difference. So U final minus U initial is Q times V final minus V initial. I said the initial position would be infinitely far away, where VI is 0, and the potential energy is also 0 at that point. And so we just get U final is QV final, or just U equals QV. So here, we take that situation where Q1 is present, we bring in a charge Q2, and we can write down now the potential energy of that arrangement. Here's how we do it. We write down first the potential at the location of charge 2, and that's V2, we'll call it V2. It's equal to KQ1 over R12. That's our simple equation for the electric potential a certain distance away from a point charge. Now we know that if charge Q2 is brought to that point, it now acquires a potential energy equal to Q times V. So what we will call U12, the potential energy associated with this pair, is just Q2 times the potential at the location of 2, and the result is KQ1Q2 over R12. Looks a little like the expression for the Coulomb force, but note two things. First of all, potential energy is a scalar and not a vector. And secondly, the denominator term is to the first power and not the second power. But it's a very simple formula that we can remember, and we can call it the potential energy that's stored in that pair of charges, or we can say that it's the work we had to do to bring the second charge in from infinity to bring it to this point near the first charge. All right, now let's imagine starting from this configuration, we bring in a third charge Q3. How much additional energy is required, or how much additional potential energy is there in that arrangement? That's easy to calculate, because we could first write down what is the electric potential at the position of charge 3 due to the other two charges, and then multiply by Q3 itself. So V3 is KQ1 over R13, and then KQ2 over R23. Add those together, that gives us the net potential at this location, so that if we bring Q3 in from infinity to that point, it gives an additional potential energy equal to Q3 times V3. And so it's the sum of those two terms. If we write down now the total potential energy, which includes U12, U23, and U13 all put together, we get this simple relationship. And you'll notice extending this to a larger collection of point charges is really easy. You simply get one term in this expression for every unique pair of point charges that are involved. And you have at least one homework problem just like this, only maybe a bit more complicated. So that's an important result. This is, by the way, physically, the result here is equivalent to saying how much work it took an external agent to put those charges into their final positions starting from infinite distance. Or we can say that it's the energy that's stored in that system. So that's an important result. Here's an example I'll skip over. We'll do that one in class, asking how much energy it takes to remove the electron from the hydrogen atom nucleus, which is a proton. Now, let's finish up this section first by talking about equipotential surfaces. These are very useful in order to understand how electric potential is related to the electric field lines in a particular charge distribution. So if you're on an equipotential surface, that means the potential is the same everywhere on it. Therefore, there's no potential energy difference between any 2 points that are on that surface. So we can move a charged particle from one point on that surface to another point without needing to do any additional work. This also means that the equipotential surface in a certain region of space is always perpendicular to the electric field lines that are present. And we can see in reference to the calculation that we did earlier, if we have a uniform electric field, then surfaces, these dotted lines appear to just be lines, but actually they represent surfaces perpendicular to the page. So for the plane through the dotted line indicated by V1, that represents a planar equipotential surface where every point on that surface is the same potential. Likewise with V2 and V3. And you should remember from before that V3 is greater than V2, which is greater than V1, because that's moving along the electric field line. Now, it's a little more complicated for cases where the field's not uniform, but let's do another case that we're familiar with. The electric field lines of a positive point charge radiate outward radially away from it. And so if we draw spheres, which are surfaces of constant distance away from the point charge, on the surface of each one of those spheres, the electric potential has the same value. And of course, the electric potential going outward along the field line will get smaller. So on spherical surfaces, we have equipotentials as well. And for, let's just say, an arbitrary charge distribution like a charged rod, we see similar kinds of field line patterns, not exactly the same as what you have for a point charge, but it's easy enough to form the equipotential surfaces by just drawing a surface that's perpendicular to those field lines at every point. And here we see they're not spheres, but they're sort of distorted spheres. So, last thing, we showed, after we originally defined electric potential difference, we showed how it was related to the electric field in a region. We're going to take that equation. First, let's talk about how to calculate the electrostatic potential when we have not point charges, but a continuous distribution of charges. And the basic strategy is exactly what we did when we wanted to calculate the electric field of a continuous charge distribution. So we have this arbitrary shaped charge distribution, and we want to know what's the electric potential at point P, a certain distance away from it. Well, we take the charge distribution, we carve it up in little pieces of charge dq, and in this case, the charge element dq is a distance r away from the point P. So that means that if we treat this infinitesimal element as a point charge, its electrostatic potential contribution would simply be k dq over r at point P. So if we integrate that quantity, we will get the total electrostatic potential at that point. The integral represents the entire volume or length or surface of the charge distribution itself. And so I'm just going to show you the generic result here, and we'll do some examples in class, but this calculation is usually much easier than when we were trying to do the same kind of calculation for an electric field. The reason is that the electrostatic potential is a scalar and not a vector. So there's no directions, there's no components or anything like that to worry about when we do this calculation for the electrostatic potential. Finally, if we have V, this is what I was starting to allude to a few minutes ago. If we already know what the electric potential is at a certain region of space, then we can find the components of the electric field by just doing some very simple calculations. And so that's kind of neat. Sometimes it's easier to first find the electrostatic potential and then from it calculate the electric field rather than calculating the electric field directly. So here's the logic behind that. The definition of electrostatic potential difference is like this. We're integrating the quantity minus E dot dl along a path. And what this implies, if you look at the integrand, summing up the integrand gives us the net result of a difference in electric potential. So the integrand must be infinitesimal changes in the electrostatic potential. So we can call that integrand dV, which is minus E dot dl. Now let's express both E and dl in unit vector notation. So E is given by Ex I hat plus Ey j hat plus Ez k hat. Likewise, dl, which is a tiny little displacement along some arbitrary direction, can be broken down into components. It can have a quantity dx along the I hat direction, dy along j hat, and dz along k hat. And looking at the dot product here, we can see that only the I hat, and j hat, and k hat terms survive. So we have this simple result. And there's a simple elementary theorem in calculus that says if you can write a differential change in a particular function like this as individual components along different directions here, then each of these components is a partial derivative of the function along that particular direction. If you haven't seen partial derivatives, don't worry, I'll explain them very briefly. But here's the result. We can identify each of these components, Ex, Ey, and Ez, as minus, because of the minus sign, minus the partial derivative of V with respect to x, minus the partial of v with respect to y and minus the partial of v with respect to z. What's a partial derivative? It's like a regular derivative, except you're taking the derivative of a certain variable, the derivative of a certain function with respect to one variable when other variables might be present. And so what you do, you take the derivative of v with respect to x, holding y and z, the other variables, constant. Again, we'll show you an example of this in class, so it'll make it a little more clear. But this illustrates that idea that if we know already what the electric potential is in a certain region of space, it's relatively simple from that expression to calculate the electric field components and therefore get an expression for the electric field in that region of space. So, hope this has been helpful, and I will see you in class.